For thousands of years, humanity looked into the night sky and imagined that we were seeing a universe that could eventually be completely understood. Ancient civilizations connected distant stars into constellations, turning points of light into stories of gods, heroes, animals, and mysterious forces. As astronomy slowly replaced mythology, generations of observers learned to predict eclipses, calculate planetary movements, and uncover the mathematical patterns governing the heavens. That progress created a powerful idea. No matter how enormous the universe appeared, its fundamental laws could ultimately be discovered through human intelligence and observation. But history has repeatedly shown that whenever we think we have finally understood the cosmos, nature reveals another layer of mystery waiting beyond our current knowledge. For centuries, Earth was believed to stand at the center of creation. Then humanity discovered that our planet was simply one world orbiting an ordinary star. The Sun itself once seemed to be the centerpiece of existence, until astronomers realized that it was only one star among hundreds of billions inside the Milky Way. Then even our galaxy lost its privileged position. Edwin Hubble demonstrated that countless other galaxies existed far beyond the Milky Way, transforming humanity's understanding of the scale of the cosmos. And then came another revelation: the universe itself was expanding. With every major discovery, reality did not become simpler. It became larger, stranger, and far more profound. Today, that tradition of discovery continues through one of the most sophisticated scientific instruments ever constructed, the James Webb Space Telescope. Webb was not built merely to produce sharper images of distant objects. Its purpose is much deeper. It was designed to investigate some of the most fundamental questions in modern astronomy by studying extremely faint infrared light from the distant universe. Positioned near the Sun-Earth L2 Lagrange point, roughly 1.5 million kilometers from Earth, Webb operates in an environment carefully chosen to keep its instruments extremely cold and stable. Those conditions allow its infrared detectors to capture faint signals that earlier observatories struggled to see. Its enormous 6.5-meter primary mirror collects light that began traveling toward us more than 13 billion years ago. By studying that ancient light, astronomers can observe galaxies as they existed only a few hundred million years after the birth of the universe. Because cosmic expansion stretches ancient visible light toward longer infrared wavelengths, Webb is exceptionally well suited for studying some of the earliest eras in cosmic history. It is not literally traveling backward through time. Instead, it is collecting ancient light that has spent billions of years crossing an expanding universe before finally reaching a telescope built by a civilization on a small planet. Long before Webb, another observatory had already transformed our view of the cosmos. The Hubble Space Telescope revealed breathtaking nebulae, helped astronomers measure the expansion of the universe with extraordinary precision, and produced the famous Hubble Deep Field by staring at what appeared to be an almost completely empty region of sky. Instead of finding darkness, Hubble revealed thousands of galaxies packed into that tiny patch of space. That single observation demonstrated something profound. Even apparently empty regions of the universe can contain an astonishing amount of structure. Webb was designed to push that journey even farther back into cosmic history. Scientists expected it to detect some of the earliest generations of galaxies with greater clarity and provide stronger evidence for existing ideas about how the universe evolved. But some of its earliest observations also raised unexpected questions. Deep observations revealed surprisingly large numbers of distant galaxies. Several appeared to contain substantial numbers of stars and organized structures at a time when the universe was still extremely young. According to standard models of galaxy formation, early galaxies should have started relatively small and gradually grown through mergers, star formation, and the accumulation of matter over enormous periods of time. Yet some of the galaxies observed by Webb appear more massive or more mature than many earlier models had anticipated for such an early period. That does not mean the Big Bang has been disproven, nor does it mean modern cosmology has collapsed. Instead, these observations suggest that some aspects of early galaxy formation may have happened faster, more efficiently, or through processes that previous simulations did not fully capture. That is exactly what science is supposed to do. New evidence does not automatically destroy our understanding. It challenges scientists to improve their models and build explanations that better match what the universe is actually showing us. Webb has also revealed remarkable information about the chemical evolution of the early cosmos. Through spectroscopy, astronomers can identify elements and molecules inside distant galaxies, including carbon, oxygen, nitrogen, and other heavier elements that were created inside earlier generations of stars. These elements could not have appeared in large quantities immediately after the Big Bang. They had to be forged inside stars and later released into space through processes such as stellar winds and supernova explosions. Their presence in very young galaxies therefore tells us that stars were already forming, evolving, dying, and enriching their surroundings surprisingly early in cosmic history. Scientists are continuing to refine their models to explain how these young galaxies could assemble and chemically evolve so rapidly while still fitting within the broader framework of modern cosmology. And this is where Webb's importance becomes even greater. Its mission extends beyond individual galaxies. It is helping astronomers investigate the enormous structure connecting galaxies across the universe. Galaxies are not scattered randomly through space. They form an immense network known as the cosmic web. Vast filaments of galaxies, gas, and dark matter stretch across hundreds of millions of light years, linking giant clusters while surrounding enormous regions of space known as cosmic voids. This structure developed gradually as gravity amplified tiny variations in density left behind from the earliest stages of the universe. Dark matter appears to have played a critical role in that process by providing an invisible gravitational framework around which ordinary matter could collect and eventually form galaxies and clusters. Although dark matter has not yet been directly detected, its gravitational effects have been observed through galaxy rotation, gravitational lensing, and the motion of enormous galaxy clusters.